Welcome warmly. Today we will cover the basics of statics on the plane. We will specifically deal with the equilibrium of flat systems of forces. And to put it even more simply, we'll learn how to calculate reactions in beams and frames. And now let's start with a very simple beam. Let's draw it ourselves. This is a field where examples can basically be invented from scratch. With this in mind, let's say we came up with such an example. Here we will have supports, respectively non-sliding and sliding. In a moment, we will draft on the side what it means that a support is sliding, and what it means that a support is non-sliding. For now, let's draw the example. We have it, and now, and also continuous load. Let's pay attention to one thing. It is immediately evident what so-called characteristic points will be in this system, and we will prematurely list and mark these points. This is our point A, B, C, and point D. Let's remember in advance what characteristic points are. These are points where new values, a new force, new moment, new reaction are introduced. The geometry changes here, but we will talk about that in frames, maybe even in this video. Now, when we have labeled the points, we look at the supports. Here, we have two of the most frequently encountered types of supports, or at least the simplest types of supports, which are non-sliding supports that give us a reaction at any angle. But most often, theoretically, it is something like this, a reaction R that is at some angle alpha. We don't know the angle alpha, we don't know the value of the reaction, so in 99% of cases, it will interest us to write it in this way. Let's say it's RBy and this is Rx, so we write the reaction as two components, horizontal and vertical, with values we don't know yet, but shortly we will proceed to calculate them. We may also have a sliding support, then we only have such a reaction, and that is immediately reaction RBy, because here sometimes, by the way, it is drawn this way, with little circles here. Although personally I don't like this way of drawing, and I think it is, to put it mildly, a bit exaggerated. It's exactly the same, of course. Now, what does it mean? It means that this system here, for this specific support, only blocks movement up-down, meaning it theoretically, in quotes, could move left-right. This specific support does not block movement left-right, but blocks movement up-down. If there's a traffic block in a given direction, we draw a reaction arrow. Right away, to avoid surprise later when we discuss supports, there is yet another way to draw these supports, namely we can draw it this way. So the support, the so-called fixed hinge support, can be drawn like this. Unfortunately, this is also found in the literature, of course, the meaning remains the same. I can't really imagine and haven't seen the hinged sliding support drawn in the same way. Therefore, we'll finish up here for now and later add the other types of supports. For this particular task, we have RB and RBx here, and only RSy here. Before we move on to calculations, we should, or rather we must, but for convenience, calculate the resultant from continuous load, or in plain language. If we have continuous load, here it is, this is the representation of loads like, for example, self-weight, type snow, or these are loads that are given per meter of the structure. So we have information that, let's write the units, this is 5 kN per meter. Notice that this is 20 kN, this is 10 kN, the moment is 12 kN times meter, and this is 5 kN per meter, which means that every meter is 5 kN. And if we have a length of 5 meters here, then at this point, the resultant is of course 5 kN per meter times 5 meters, which is 25. And now, because later we'll be dealing with continuous loads of shapes other than rectangular, such as triangular continuous loads, it's best to remember that this is the area of the figure, where 5 kN per meter is the height, and 5 meters is the width of this figure. And the resultant is always centered at the centroid of the figure, which for a rectangle is simply halfway. So, for simplicity, to avoid overthinking later, we write 2.5 here. 2.5 implies meters, which is the kN. And now we assume a reference system. The reference system can be assumed arbitrarily, however. I personally suggest adopting this one. XY, the moment can be in statics and equilibrium emphasized as assumed arbitrarily. A more correct one is a counterclockwise positive moment. And now we will assume a clockwise positive moment here, mainly because I am personally more accustomed to this. And now for every flat system we formally have 3 equilibrium equations. This is the sum of projections on the x-axis, or in plain language, this is the sum of horizontal forces. The sum of projections on the y-axis, in other words, the sum of vertical forces, and the moment at any point. But really, To simplify calculations, we assume these are support points, meaning we can accept that this is truly any point. I might say, for example, that here is point E, which is exactly in the middle, and I can calculate the moment at this point, and it will be just as valid an equilibrium equation as any other. However, usually it's simplest to take the moments at the support. In more difficult examples, we will do a bit of maneuvering, but for now I'll talk about the really simple ones. As you can see, we have only one horizontal force, it's Rbx. Therefore, Rbx must be equal to 0. Because this reaction is not activated in any way, so to speak. We don't have a horizontal force, so we also don't have a horizontal reaction, because there's nothing to react to. On the y, we have minus 10 plus RBI. Notice, because we accepted y upwards here, we quietly assume here that what goes up is positive. What goes down is negative. We only consider forces, which means we do not consider moments 12. We only take the force 10 downward, hence minus 10. RB upward, hence RB on the positive. And now we will have minus 25 plus RC minus 20. We see that the equation, albeit surely correct, unfortunately does not allow us to calculate anything because we have two unknowns. From one equation, we're able to calculate one unknown in principle. Therefore, let's leave this equation for now and proceed to the next one, which is the sum of moments at point B, and now how to calculate moments. Simply put, at this point, we mainly focus on the reference, the point with respect to which we calculate this moment. If this is point B, then we accept at this point that everything we do with respect to this point. Because we assumed right-turning moments are positive, meaning we essentially assumed our positive z-axis goes behind the page, because the moment we calculate is essentially moment z. In spatial systems, we will talk more about this. For now, you can remember, it will be useful later. However, most importantly here, what matters? This is the moment with respect to point B, so when we look at 10, we'll see that this 10 would rotate the system with respect to point B. Oh, like this, which means counterclockwise, or in other words, left-handed. We can imagine it like a seesaw. We have a support, here we have the rest of the system, and we imagine how a force applied here would rotate the seesaw, as if there was a weight here. Well, it's clearly visible that it would rotate like this. Since this is opposite to the reference system we've adopted, we write that this is minus 10 times 2. Why times 2? Because the moment is force times arm, in a simplified way. By the way, because in reality, it's a cross product. However, we'll assume in these tasks that each time we'll have force on the arm perpendicular to it, with respect to a certain point O. So we assume that the arm is always perpendicular to the force vector, and this is the distance between the point of application of this force and our examined point. That's why we have minus 10 times 2. 10 kn 2m, this is exactly what we have here. Then we have what happens at point B. RB passes through point B. First of all, forces passing through the examined point certainly don't create moments. Not because I said so, but because if something passes through a point, with respect to which we check rotation, it won't rotate it. If here, exactly where we have the seesaw point, with respect to which the seesaw rotates, we apply force, it won't cause the seesaw to rotate. However, we take this moment, and it is immediately right-handed. Clockwise, we give plus 12 without distance, because it's already a moment. It can actually be drawn as a moment going through the paper. Next, we have continuous load. We take the resultant on the plus side. Now, why on the plus side? Because if it were here, it would rotate our seesaw in this way, meaning this point would go down in relation to the center of rotation. So we have plus 25 times 2.5. Why 2.5? Because that's the distance. We're always in the center of gravity of the load, which is here halfway. Then we have minus RC, I think we all know why, minus times 5, and finally plus 20 times 8. Because this is the total distance between point B and point D. 5 plus 3 equals 8. That equals 0. Here we have one unknown RCI, so we can quickly calculate this RCI. Minus 10 times 2 plus 12 plus 25 times 2.5 plus 20 times 8. Maybe let's write this down twice here. It comes out to 214.5, which is simply the sum calculated on a calculator, for all these elements here not containing RCI. Minus 5 RC equals 0. We move this to the other side. We get RC equals 214.5 divided by 5, and that gives us 42.9. Remember, these are Kn. And great, we have calculated RC, and now we can return to the sum of y. We will then calculate RBe because we have it minus 10 plus RBe. This is the equation, right? Minus 25 plus RCy minus 20 equals 0. We substitute RCi, calculate on the calculator minus 10 minus 25, plus 42.9 minus 20. We get minus 12.1 comma move to the other side. RB equals 12.1 kN. This is one way to calculate this. Of course, because these equations are arbitrary, so the order is also somewhat adjustable. Slight possibilities of change. Besides, we will see in subsequent examples. However, here we will just do a check. Well, okay, we calculated these reactions, but it would be nice to know if we calculated them correctly. We have the freedom of how we can verify this. We can choose any equation that we have not used before, so it really leaves us with the sum of moments at another point. But the point relative to which we will calculate is arbitrary. It's good to choose a point that takes into account all loads. So a point where no reactions intersect, no forces intersect. Let's take our E, for example. Well, let's erase something. Maybe let's erase this to have more space. The principles, of course, remain the same. And now, what do we have here at point E? So let's go one by one. Relative to point E, we have 20 times 1.5. Positive, we see it. Plus RCi times 1.5. Notice that even though these forces, this one is down, this one is up, both are positive for the moments with respect to E, because they lie on two different sides of this point. RC times 1.5 comma, of course. Here we have minus 25. And note that we are interested in the distance from the point, where the force acts to point E. It is 2.5 plus 1.5 comma, which equals 4 meters. This is tau, right? Here we have 4 meters. Then we have plus 12. Again, without distance because this is already a moment. Plus RB times 6.5 comma because of the distance from B to E. And then minus 10 times the distance from A to E. 2 plus 5 plus 1.5. 8.5 meters. In accordance with the drawing, indeed. And now we check. We can actually input this directly into the calculator because we know that RCE is 42.9, RB is 12.1. So we write on the calculator, 20 times 1.5 plus 42.9 times 1.5. Subtract 25 times 4. Add 12. Add 12.1 times 6.5. Subtract 10 times 8.5. We end up with 0. You can check this in your spare time on a calculator. We write that the left is equal to the right. And this really concludes the task. This is everything that needed to be calculated here. The content of the task was to calculate reactions. So these are all the reactions that can be calculated for this setup. This was the simplest example of a beam. Now let's move on to a slightly more complicated case. We will keep the reference system because we won't change it. We will also keep the cheat sheet. And now, let's do a task where a little more will happen. We will make a hinged beam. And additionally, just for fun, we will fix it on one side. Here we will give 4 meters. Here we will give 3 meters. Here we will give a moment of value 10. Here we will give forces of value 6. We will make continuous load a triangular one for a change, so it's not always the same. Value, let's say 12. And now we have 2 new elements coming in. We've already talked about continuous loading. The fact that it is triangular, that really doesn't change anything. And now we have a new element coming in, which is the hinge, and we have a new type of support, which is full fixation. Full fixation gives us 3 reactions, or actually 2 reactions in a moment. So just like before, we have a vertical reaction, horizontal, but in addition, we also have the so-called fixing moment. And right away, so nobody is surprised later, there are also sliding fixations, meaning there is a fixation where, for example, we allowed vertical displacement. If we allowed vertical displacement, we actually know what the reactions will be. There will be a horizontal reaction in a moment. There won't be a vertical one. Because if we've allowed displacement, then naturally a reaction won't appear, right? Next, we will have, of course, it can also be drawn like this. Because the one difference here is that we've allowed horizontal displacement, so vertically we have a reaction, and the moment remains unchanged. And now that's one thing. Now the second thing is the moment. The second thing is the hinge. And now when it comes to the hinge, let's quickly describe it as ABC. There are really 2 ways to treat it. Firstly, we can say that we get a new equilibrium equation, a moment concerning the hinge, but for one side. Only this really comes from the fact that the hinge can divide the given system into two parts, based on how many components are present on both sides of the hinge, or how many so-called subsystems we can create. Here there are actually two subsystems, because if we divide it by the hinge, we actually get the same either way. But of course, we can't just say, well, I divide it and there's nothing. In fact, if we are breaking something in the joint, then we must replace this joint with reactions. So, in fact, it has now been replaced by the reaction RBy RBx. Of course, we remember from physics that when we have such a situation, meaning interaction between two bodies, then to the second body we must attach opposing forces, the same in value but opposite in direction. Everything else remains unchanged. Ray RCy, RCx, RCm. But now pay attention to one thing. Here we had a moment. A moment is always clearly on one side or the other of the joint. It cannot be that the moment is exactly in the joint. However, force 6 is actually exactly in the joint. A force can be applied to the joint. This doesn't hinder us at all. Now we have a choice. Regardless of whether we assume it belongs to the upper or the lower body, lower or upper layer, the solution will be correct. Let's assume it belongs to the upper, because it doesn't really have any deeper logic. Here we have continuous loading. Let's recall the rule. I take the center of gravity. If someone doesn't remember the center of gravity of a triangle, I remind you it is 1/3 from the higher side, 2/3 from the lower side, in this case from 0. So here we have exactly a division into 1 meter, 2 meters, because 1/3 of 3 is 1, 2/3 of 3 is 2. Here we have a resultant that has the same value as the area of this figure. The area of the triangle is 1/2 times 12 times 3. 6 times 3 will be 18 as nothing else, but let's check again. We will not assign specific units here. At this moment, it doesn't matter much to us. We just want to calculate these reactions. Now, if in the task description it is simply said, please calculate the reaction, then for a beam of this type, it is much simpler not to use this breakdown, because here we would essentially have to additionally calculate these RBI, RBx. Just write it out for the entire body, sum x. Of course, we start with the simplest equation. We see that RCx is the only horizontal force, hence it nullifies. And then we take the moment at point B on the left side. We can denote this as the moment at point B on the left. We can denote it as the moment at point B for the first subassembly, it doesn't matter. Using what we learned previously, we quickly compute this moment. This is Rakes times 4. Subtract 10. And that's it, because the 6 passes through the point in question. RB passes, RBx passes. This equals 0. Ray equals 10/4. 10/4 is 2.5. We can also write it down this way. And now, if we calculate for the entirety, at this point, it will be easiest to sum up say y, because we have Ray minus 6 minus 18 plus RCE. For simplification, I will rewrite this 18 here. Here 1 meter and here 2 meters. 2 meters. From this we derive RC. I will use a calculator for this. We substitute 2.5 for Ray, subtract 6, subtract 18. I get 21.5 negative, but I'll move it to the other side. So it just remains as 21.5. Great, I have RC. And now, what do we need to solve the entire problem? RCM, which is the support moments at point C. It's the sum of moments at the point. And now, of course, at any point. Let's do it at point B on the right side. Or in other words, at B for the second subassembly. It's as if we only have this part here, and we're calculating the moment at this point. So we have 18 times 2. Subtract RC times 3. Add RCM equals 0. Did I forget anything? I don't think so. So from this, RCM equals 18 times 2. Subtract 21.5 times 3, resulting in minus 28.5. But I move it to the right, so I have 28.5. And that effectively completes the task. But it's always worth checking. Let's perform a check. And contrary to what I said recently, to always operate with respect to the point, or at least try to work with respect to the point, where no reactions intersect, since we've been working with respect to point B the whole time. Let's say we work with respect to point AC, for example. Why not? The sum of moments at point C equals 0, and we get minus 18 times 1. Note that this is for the entire system now. I'm not writing that it's from the left, right, for 1, for 2. Therefore, this is for the whole. Alternatively, you can state that this is the sum of moments at point C. C as in comprehensive, but I think that's unnecessary. Subtract 6 times 3. Subtract 10, add RBy times 7. What's missing? RCM, of course. Despite calculating at point C, we include RCM because the moment does not need additional distance. This is already a moment. And we have minus 18 times 1, minus 6 times 3, minus 10, add RBy, which is 2.5 times 7, add RCM, which is 28.5, equals 0. Left equals right. Of course, you can verify this at your leisure to make sure there's no error in these calculations. If we were to insist that we want to calculate for two separate subsystems, it really depends on the type of problem we are facing. Here, it was more convenient to calculate for the whole system without breaking it down into subsystems, just doing the moments on the left and right sides. But if we insisted on calculating for the subsystems, it would look like this. RCX, and so we do it for the whole, because here it would be redundant and creating non-existent entities if we wanted to calculate this X for two separate subsystems. However, the calculation process will be very similar. We mark it. For the first subsystem, the sum of moments at point B equals 0. We add this one so that we won't forget later that it is for the first subsystem. Of course, this is the equation itself. There is nothing new here. RBy equals 2.5 kn. Next, we calculate the sum of moments at point A. For example, completely arbitrary. Whichever equation we use now with sum y, we will also get the correct result. But moments are more interesting, and students usually have more problems with it. So let's do what is harder for practice. We get RB. We didn't calculate RB in that task. If they asked us to calculate the reaction in the joint, then we would have to. We got 3.5, RB to the other side, so it actually comes out to 3.5. And this is actually the entire first subsystem. Alternatively, if we are very uncertain about our solutions, then we take RBy plus RB minus 6. That means we take sum y and check to make sure that it actually matches. But 2.5 plus 3.5, calculating mentally, we see that it indeed balances with a load value of 6, so it is all right. For now, everything is the same. Alternatively, sum x here everywhere for the first subsystem, so as not to forget about it. And on sum x, we see that RBx is equal to 0. That's if we didn't want to calculate anything for the whole. Then we take the second subsystem. For the second subsystem, pay attention. We have RB and RBx. If we have RB and RBx, then the simplest sum x equals 0. We write that for 2. So RCX formally equals RBx. Pay attention. Two opposing forces will cancel each other out. They could just as well write minus RBx plus RTX equals 0, but it is exactly the same. And of course, it is still 0. Then we can make sum y, for example. Here again, the order is arbitrary. And we have minus RB minus 18. Add RC equals 0. From this, we calculate what we haven't calculated yet in this method, which is RCI. So we have 18 plus RB, which is plus 3.5, 21.5 comma, and you won't believe it. But it still comes out the same as in the previous method. And with the moments in the point, again, it is an arbitrary point. Let's do it, for example, at C, because why not for the second subsystem? We receive, of course, RCM minus 18 times 1, minus RBy times 3. This equals 0, and from this RB equals. Sorry, RB, we already have from the previous subsystem, so RCM equals, of course. In RCM, this equals, at 18 plus RB, which is 3.5 times 3. We get 28.5, and it is exactly the same solution that we obtained with the previous method in quotes. I won't do the verification anymore. The verification would be the same, and when we divided it into subsystems, it's best to do the verification for the whole subsystem as well. So don't even think about doing just a verification for the subsystem and deciding it's okay. We always do the verification for the entire system to avoid any mistakes for sure. Thanks a lot.